Yeah. So good evening, friends. Today we'll discuss on remote sensing and GIS applications in geosciences. And myself, IIRS Chatterjee. I am from Geosciences Department of Indian Institute of Remote Sensing. So to begin with, I am just changing my slide. Just wait, yeah. So remote sensing, you know what is remote sensing? The definition of remote sensing is already known to you. So remote sensing is the science of sensing the Earth and planetary objects remotely from a remote distance based on electromagnetic radiation received from the objects. So you need a certain platforms like satellite, like aircraft, or like a drone, from where you can receive the electromagnetic radiation which is coming from the objects. And in geosciences, there are many applications. For example, geomorphological mapping, lithological or rock types mapping, geological structures. These are the basic applications. And other applications, those are very focused applications. They are like mineral and hydrocarbon exploration, groundwater prospecting or groundwater modeling, then construction material exploration, engineering, geological investigation, environmental impact assessment, particularly geo-environmental impact assessment, geological hazards, mapping, assessment, monitoring, and modeling. And there are many more applications. But you know, remote sensing is more effective and more powerful in synergy with complementary data sets such as geophysical data, geochemical data, subsurface data that can be available by these boreholes, by some kind of geophysical logging, and also ground truths. So ground truths or field-based data also very, very important. Now, you know, any remote sensing image, whether you generate from any satellite data, from airborne data, or from drone, any image of the Earth's surface, it represents a stack of many thematic layers, many kinds of information. Like there is information of topography, vegetation, land use or infrastructural information, then soil, then geomorphology, rock types, and geological structures. So all kinds of information are combined in an image, maybe satellite or airborne image. Now, from all kind of information, it is the job of a geologist, remote sensing geologist, I should say. So we need to separate out the geological information using direct and indirect signatures. And what are those geological information? They are geomorphology, lithology, and geological structures. These are the three basic geological information that we need to separate out, which is available on the image, either in the form of direct signatures. Sometimes direct signatures are not very prominent, so we need to rely on the indirect signatures. So using these direct and indirect signatures, with the remote sensing geologists, we need to separate out this geological information. And how we do that? We do using this satellite image interpretation, that is known as visual image analysis, and digital image enhancement and feature extraction. Now, in the visual image analysis, you know, there are certain interpretation elements. Okay, so what I told you that your direct interpretation elements are direct signatures and indirect interpretation elements. So they are like photo and image elements. They are the direct interpretation elements, and it includes tone or hue, texture of the image, then shape or form of the objects, size of the objects, pattern of the objects, and association of different objects. Then comes these indirect interpretation elements. They are terrain or geotechnical elements. They include landform, drainage, vegetation, and land use. Now, we need to interpret based on these direct signatures and indirect signatures, and we'll have different kind of derived information. Now, we need to convert them Now this convergence of information from these photo or image elements, those are the direct interpretation elements, and this indirect interpretation elements like the terrain and geotechnical elements. Okay, this is the key to a successful visual interpretation. So however your image, your map, or your feature extraction is successful, it depends on how you can interpret this direct and indirect signatures and how you can convert them. So that is very, very important. Now you see here, just for example, I will give you some illustration here, like tone or hue. You know, tone means it is the relative brightness of the objects on an image. And that image is a black and white image. And hue is the color. When this image is a color image, and that is expressed in intensity hue saturation system. Okay. So here what we have shown here on the right side, this is a black and white image, but it is most important when you will be interpreting the image texture. And what is texture? Texture is defined as the frequency of tonal change. Okay, and it is the result of the composite appearance of the unit features. Now you see in this particular illustration, here the tone is more or less, it is bright to moderate tone, isn't it? It is not dark after all. But here the texture is different at different parts. Tone is not much different, except in some areas there is very bright tone. Okay, but other than this entire this image, here you see that the texture is very different. In the upper part, the texture is very smooth, fine texture we call it. In the middle part, very rough appearance, isn't it? It's a coarse texture. And in the lower part, if you see, there are striations, isn't it? There are line-like striations and these crisscross striations, isn't it? So from that, we can interpret that what kind of rock types are there. Okay. Here you see, we'll come back to this particular illustration. You see, this is very, very soft kind of rocks. That is why the texture is smooth, and it is essentially sedimentary rock. And here it is very hard and compact, but the scooping out effect is very, very prominent. Okay, and this is the igneous rocks. Not only igneous, it is a massive rocks. No, igneous rocks are generally massive rocks, except these extrusive igneous rocks like lava flows. And here in the lower part, it is the metamorphic rocks. And what are these striations? The striations are the regional foliations. They are the regional peak plains. So all along these peak plains, what happens? There are the weathering and erosions is more prominent. Okay, and that is the reason they are differentially eroded, differentially weathered and eroded, and that gives you this kind of striated appearance. Now coming to other interpretation elements like shape or form. Okay, this is like a child also can identify based on certain this typical shape, like a river. Anybody can identify, isn't it? So this is a river based on this meandering nature. This is a river, although this meandering nature is a little distorted, but even then it is a meandering nature only, carved nature of the river. On that, anybody can identify, you don't need to be a remote sensing expert that it is a river, isn't it? The pattern, this pattern is defined as the spatial arrangement of the features, and there will be different kind of patterns like parallel patterns, like orthogonal, like concentric, like banded pattern, a radial pattern, rectangular pattern. So different kind of patterns of the objects. Here, what kind of pattern you see here? Banded. It's a parallel arrangements of the bands, isn't it? And this is a little bit curved also. So from this pattern, we can interpret that the rocks are alternately arranged. One is hard rock, another is soft rock, hard rock, soft rock. This is alternately arranged. Hard rock, it does not support vegetation. It does not have soil, okay, because it is hard and compact. No soil moisture, no vegetation, so it is barren, bare rock. So it is bright. And the soft rock, there is soil and soil moisture, supports vegetation, so it is dark in the black and white image. This is panchromatic range. Here you see the pattern, different kind of pattern. You can see this is crisscross pattern. Here is a very, very regular, these patterns of these weak planes. And here you see spatially extensive weak plane, isn't it? So all this pattern help us to interpret that there are some geological structures. There are either lineaments, they are either joints, they are fractures or faults. Essentially, they are the geomorphic features due to the geological structures. They are the lineaments and faults. Here you see there is some curved pattern. So this is a folded structure. So from the pattern itself, you can interpret many things. Now see association. So based on the association of different objects, you can interpret what is the other objects are. Okay. So for example, if I ask you, what are these white threads, bright threads? Very difficult to identify what exactly these threads are. Okay. But now I am coming to this full view. Okay. Just allow me a few seconds. Yeah. Now you see that. So these white threads, I asked you, what are they? It is a little difficult to you unless you know that. Now, if you see that, all of you can tell what are these features. These are the volcanic flow lines, lava flow lines, isn't it? So these are the volcanoes, volcanic cones. From here, the volcanoes, these lavas are erupted, and the lavas are flowing here. Now it is solidified. So this is the association of these features, that is the volcanic cones. When you can see many other features, the pyroclastics, isn't it? Then the lava flow, this lava flow lines, so many things you can interpret. So slide transition is taking little time. So morphology, these are the these indirect interpretation elements. Okay, so morphology basically it is how it is expressed on the surface. So the geology of an area is basically reflected in the morphology. And here you see there's a ridge valley topography is the morphology of this particular area. And when does it occur? When there are the rocks of the differential hardness. One is hard, another is soft. So hard rock will give you the ridges and the soft rock will give you the valleys. So differential erosion of the hard and soft rocks, it gives you this ridge and valley topography due to differential weathering and erosional processes. Isn't it? Now drainage. Drainage helps a lot to interpret the geology of an area. Okay, like the channel form, for example. The channel form, this is a cross profile, that is the cross section, and the longitudinal profile, along the river, along the channels. So both the features are very, very important to interpret. For example, if the cross profile is V-like, then we can say the substrate is coarse-grained or medium-grained. And when you see this cross profile is U-like, U-shaped, then we can say the substrate, that means the river bed is fine, it's made of fine-grained materials, like shale or clay kind of materials. And the longitudinal profile also helps a lot. Then drainage pattern, then drainage morphometric parameters, like there are many morphometric indices or morphometric parameters, like drainage density, like stream frequency, bifurcation ratio, drainage texture, ruggedness index. So all these indices help us to interpret this geology of this area. How much is the structural control, what is the rock types, so all these things you can interpret using these drainage parameters. And drainage pattern itself, it tells you what is the geological, your structural control, what is the rock types, what is the attitude of the rocks. So all those things you can interpret from the drainage pattern. I'm coming to that. The next slide. So, and other these interpretation elements. So this drainage pattern, I'll come after 2 slides. Okay. Now vegetation and land use, they are also very important interpretation elements. Okay. So like vegetation lines, or if you find in an area the vegetation lines, otherwise it is a barren area. So you can say that this is a weak plain, it is a fracture. Okay, all along that there are soil has formed, there is soil moisture is there, and vegetation has grown. So that is the reason this is a geological structure. It is a lineament, so that you can identify. Similarly, based on this vegetation cover, also you can say that there are these rocks are of soft rocks, or what kind of rocks are there. and in the adjacent area there is no vegetation or vegetation is very sparse, you can say that the rock types are hard, compact, isn't it? So indirectly you can interpret. Similarly, land use also help us. Land use tells us what is the slope of the terrain, whether the soil is there or not, whether the soil moisture is there. Okay, so depending on whether you are getting in a hilly area, for example, hilly slope, if you find there are these agricultural practices, then you can say that the soil is there, soil moisture is there, so your slope is gentle, isn't it? So this kind of information you can indirectly infer. Similarly, if you find there are some settlements are there, then you can say that it's slope, the stability of the terrain, and the rocks are comparatively hard underneath. Otherwise, nobody will construct house there, isn't it? Now, coming to different rock types, that particular, this example I have shown earlier as well. So let me increase this view. Okay, so see here in this, so as I already explained to you, that this on the upper part it is a sedimentary rock, in the middle part it is a igneous rock, and in the lower part it is a metamorphic rock. And why? How we interpret that? See, what is igneous rocks? What is their characteristics? Igneous rocks are homogeneous, they are massive, they are hard, they are compact, they are very resistant, they do not have any bedding. So no bedding means no layering. So no layering appearance you will find in case of igneous rocks, except in case of the lava layers, isn't it? And so what kind of appearance it will come on the image? This texture will be coarse texture, and there will be characteristic joint pattern can be visible. So based on this landform, this joint pattern and the texture, you can interpret that is igneous rocks. And here the texture is very, very important to interpret. This is igneous rock. Now what is the sedimentary rock? Sedimentary rocks are deposited rocks. Okay, the material is deposited, they are consolidated, they are compacted and hardened, and finally the sedimentary rocks are formed. So the sedimentary rocks are soft and bedded. So there is a layered appearance is very, very important. They are easily erosible, and they are very easily dissected, isn't it? Because weathering and erosion, they are dissected very easily. And so what kind of texture you will find there? The texture will be smooth, so fine texture. And because the sedimentary rocks are layered, so one layer of rock may be very hard, another layer may be soft. So there will be differential weathering and erosion that can give you ridge valley topography. And there are many other landforms, like in case of horizontally bedded sedimentary rocks, there will be one set of landforms like your plateau, mesa, butte. In case of dipping beds, this again, this is what is the deep amount, that is also important. In case of gently dipping beds, there will be the landforms like cuesta, where the deep is steeper. You can get hogback, you can get the ridges. Okay, so these landforms and this texture and this your tone help you to interpret the sedimentary rock and the dissection as well. And metamorphic rock, as I already told you, metamorphic rock means they are under pressure and temperature, isn't it? So they are metamorphosed and they are deformed. So because of the process of metamorphism and deformation, there will be weak planes will be developed. Parallel weak planes, those are regional in nature, will be developed. They are nothing but regional foliations. The rocks will be deformed, and deformational structures like faults will be developed. Okay, so based on these kind of features, you can interpret this is a metamorphic rock. So here you can see there are the weak planes are very, very prominent. There are the regional foliations, and from these regional foliations, the striated appearance you can find on the image, isn't it? The striations are very, very clear. So from that you can interpret that this is a metamorphic rock. Now here you see I have given a set of these three different rock types like igneous rocks. You see here igneous rocks you can very easily interpret. This is the volcanic rock. This is also volcanic cone, but different kind of these volcanic materials here, isn't it? And here you see this is extrusive igneous rock. Volcanic rocks are extrusive igneous rocks. And here you see this is the dikes. This is the intrusive igneous rocks, isn't it? So that is intruded this through the host rock and occur as the wall rock, isn't it? And here you see this is the sedimentary rocks. This is a layered appearance is very prominent. Ridge valley topography is there. And you see dissection is very much here. There are faults, there are a lot of drainage cutting across these beds, isn't it? Here you can find this drainage. So this is sedimentary rocks. And on the right side, both the illustration, this is metamorphic rock. Here you see the regional foliations and fractures. This is the gneissic rocks, granite gneiss. And here you see this is the schistose rocks. And you can find this your folded structure very clearly. And these are the regional schistosity, regional foliations. And this is the fold. So from that, you can very easily interpret that these are metamorphic rocks. Now drainage pattern, as I told you that after 2 slides, I will explain to you how drainage pattern help us to interpret geological information. Like you can interpret the rock types, you can interpret the attitude of the rocks, you can interpret the geological structural control. Like if the pattern is like dendritic, like a tree, okay, this dendritic comes from dendron. So like a tree pattern drainage, if it is like this, then we can say these are horizontal sediments or sedimentary rocks or uniformly resistant crystalline rocks. Okay, and the slope is regionally very, very gentle. Okay, so you can interpret what are the rock types here. If the pattern is parallel, okay, this one, then you can say that here the slope is moderate to steep. So it is topographically controlled. If you see, this is the trellis pattern, parallel long drainage, and there are short drainage are many, numerous, and it is across this long drainage. This is trellis pattern. So trellis pattern tells us either here the rocks are homoclinally dipping in a particular direction, they are dipped, okay, or they are the folded sequence. Alternately, this syncline and anticline. Along the axis of the syncline, this is the long drainage, okay. On the slope of the syncline or anticline, there are the short drainage. Here the axis of the anticline, here is the axis of the syncline, okay. Now here in rectangular drainage, what you interpret from here is the orthogonal joint pattern, okay, perpendicular to each other, 2 sets of joints, that gives you orthogonal this drainage pattern. And if you see radial drainage, then you can very clearly, you can tell that it is a volcanic domes, or it can be a residual dome also. But if it is not purely radial, but it is annular, so you get this kind of pattern, major drainage like this, then it is go down. In this pattern like this, like the onion-like pattern, okay. So this pattern, this tells you that it is a structural dome, okay. So you know antiform, synform, okay, anticlinal structure or fold. So it is a dome-like this your feature, or over this kind of drainage develops. So many things you can interpret even from the drainage pattern itself. Now from the drainage density also you can interpret what is the rock types. In drainage density, we use the criteria like what is the resistance of the rocks, what is the permeability of the rocks. Permeability means how much water can percolate down through these rocks. This is the permeability. Okay. If the permeability is high, here the surface drainage will be less because the water which comes due to rainfall, okay, the surface water will go down to the underground, to groundwater, but we can pump out for drinking, for industry, for irrigation, isn't it? So these are the criteria, the hardness or resistance of the rock formation, permeability of the rocks, then the topographic slope, and then the climate. Climate means essentially rainfall and to some extent temperature. So based on these criteria, we can say that what kind of rocks are there, okay? So essentially the hardness and the permeability is most important. Now again, you can see here, can you interpret what kind of rocks it could be? This is a sedimentary terrain. Now you see here, I have again made the full view. Now you see here, this is the interpretation. Okay, you see here, this drainage density is very, very high. Okay, so it is a fine-grained rocks like shale or clay kind of rocks. Whereas here the drainage density is not that dense, no? It is widely spaced. So here the rocks is sandstone. So you can interpret the different rock types, and while you are interpreting the rock types, you are also interpreting the geological structure. You can see here there is a folded structure. Okay, so this how you can interpret from the drainage density. And what is drainage density? Drainage density is the ratio of the drainage length by area. You can get it for the entire area, but for this kind of interpretation you have to do in grids. So for each grid you have to see what is the length of the drainage and what is the area of the grid. And if you do that, This ratio tells you this is the drainage density. Okay. Now, if you interpolate this drainage density of the grids, then you will get the drainage density surface. Now, from this drainage density surface, you can density slice it, or simply you can interpret this, and based on this interpretation, we get this is the what are the rock types it could be: sandstone, shale, again sandstone. Okay. Now, geological structures, these are developed due to deformation. Okay. What are these geological structures? They are folds, they are faults, and they are the lineaments and unconformities. How remote sensing helps to identify the geological structure? Because remote sensing gives you a synoptic view. It gives you the regional view of the outcrop pattern of the area. So if you go to the field, you can see only a particular point, but you cannot see what is happening here, what is happening here. But in a remote sensing image, you can see the entire picture. That synoptic view is available with you. And from this synoptic view of this feature, you can very nicely interpret what is the geometry of the structures, what is this type of the structures, what is the attitude of these beds, all kinds of interpretation you can do. Okay, I will explain more in the next slide. Now you see faults, for example. Faults means what? It is the fault of the earth. Okay, it's not fault, our fault. So due to some kind of this tectonic stress, this earth is getting faulted, displaced. It is first rupture is taking place, and along this rupture, displacement of the rocks is taking place. And this displacement of the rocks, you can very nicely see in a satellite image. In the field also you can see, but it is a point-based information. Okay, so macro scale information what you can get from the field. But in remote sensing image, you can interpret the regional picture of the geological structure. Here you see is an exposed folded structure, and this folded structure very nicely you can interpret the geometry of the folded structure. Here are certain landforms are there. You can see these are the landforms, triangular facets, isn't it? Here are small size triangular facets, and here it is the large size triangular facets. But you see here these triangular facets are known as the flat iron, like the iron shaped this your feature. This iron, this for pressing our clothes. So it is similar. This is also similar to the iron. So iron shaped this feature helps us to interpret this structure. How it helps us? This flat iron points opposite to the deep direction of the bed. So here you see this iron is pointing towards this. So that means the beds are dipping towards me, towards the observer, isn't it? And where this flat iron is broad, the deep is central. Where the flat iron is narrow, the deep is steep. So by interpreting these flat irons, this deep direction and the amount of deep can be interpreted, and the geometry of the faults can be interpreted. Now you see, so in the previous one, what kind of structure it is? It is a domal structures. Okay, it's a doubly plunging fold, domal structure. But in this case, it is a non-plunging. But how we interpret it is a fold. You see, there is a symmetrical repetition. In the center, there is one kind of rocks which is very soft. Okay, this shale or clay kind of rocks. On the other side, this is your bedded sandstone, alternately bedded sandstone and shale. Mostly, essentially, it is sandstone. This is tip of sandstone of the northeast, this India. And then there is another kind of rocks that is again soft, that you can see from the dissection by the streams. Okay, so from this symmetrical repetition, we can interpret there is a folded structure, and the geometry of the folds we can interpret from these landforms. And these landforms are nothing but the flat irons. So from the flat irons geometry, we can interpret what is the deep direction and what is the deep magnitude. And we can interpret here that it is a synformal structure. This is dipping towards each other. Dipping towards each other, it is a synformal or synclinal structures. But that is a non-plunging one. It is not, fold is not now plunging. Plunging, and geologists know that, but other people may not be knowing that. So plunging means it is horizontal. Okay, this orientation of the fold is horizontal. Whereas if you see here the fold is plunging fold. So you are getting a closure. So this kind of information you can extract very nicely from the remote sensing image. You can get it from the field, but you will not get very precise information, isn't it? Because you have point-based information. Then you have to interpolate. Sometimes in the field, this geolocation is not very correct. and we do not have a very dense this your sampling. So while we are interpolating, so we make some mistake, isn't it? We get a broad picture, but very precise your picture of the geological structures, their geometry, all those things we can get very nicely from the remote sensing images. Now you see, what is this? Here you see the river, a stream suddenly gets straight, rectilinear, isn't it? So there is an anomaly in the river. It becomes straight here. There is an anomaly all along this line. There is a soil infilling all along this, isn't it? So there is a weak plane which is filled up by the weathered material, weathered soil, isn't it? There are other anomalies. You see the vegetation is curved. Vegetation is curved. All these things are very clear-cut indicators that there is a fault like this. There is a fault like this that we can interpret. All along this line, there is a geological fault. It is a ductile shear. There is no offset has taken place yet, but it is basically we can call in remote sensing interpretation, we can call it is a geological fault. Okay. Now you see, there are many weak planes. There are faults like it is a fault. These faults are spatially extensive, and there are fractures. Those are random in nature, randomly oriented. These are the fractures, and here you see regular pattern of the weak planes, crisscross, orthogonal pattern of the weak planes. These are the joints. So these are the joints, planes. These are all weak planes. Okay. For a layman, these are all fractures. These are fractures without displacement. This, as well as this. But for a geologist, it is a joints, and these are fractures. They are different. Okay. And this one, it is not a fracture or a joint, but it is a fault. So first it is a fracture followed by displacement of these two blocks. Okay. Now coming to the thermal remote sensing, you know this the electromagnetic this spectral region of the thermal remote sensing is 3 to 35 micrometer. So 3 to 35 micrometer region is popularly called the thermal infrared region. Okay. So out of that, 8 to 14 micrometer is very much used for terrestrial sensing. Why? Because at ambient terrestrial temperature, the peak of the Earth's blackbody radiation, it occurs around 9.7 micrometer. And you see 9.7 is in the middle of this 8 to 14 micrometer. And why 8 to 14 micrometer? Why not 7? Why not 15 or 16? Because 8 to 14, there is a atmospheric window. There is an atmospheric window in 8 to 14. Okay. So you see here, this is 8 to 14 and this is 3 to 5. So 3 to 5, 8 to 14 micrometer, there are the atmospheric windows there. And 8 to 14 is very important for the Earth sensing, thermal sensing of the Earth surface. Except for certain high temperature objects like volcano or like the coal fire or forest fire, you need the shorter wavelength data. Okay. And why thermal remote sensing is important? Because most of the geological materials, particularly the silicates and other kind of these clay minerals as well, they have your absorption peaks. Okay, they are spectral absorption peaks in this region only. You see, there are many your typical absorption peaks you can see in these rocks in this region. Particularly in case of these igneous rocks, there is a characteristic absorption peak in 10 to 12 micrometer. And this absorption peak is known as the Ristrelan band. And that occurs due to stretching vibration between silicon and oxygen. Silicates is made of silicon and oxygen, isn't it? So between silicon and oxygen, there is stretching vibration is happening. And from this stretching vibration, so this kind of absorption peak is developed. Here you see, depending on the percentage of the silica in the rocks, this absorption peak shifts. If the silica percentage is high, then what happens? This absorption peak is close to 10 micrometer. And when this silica percentage is low, then this absorption peak is close to 12 micrometer. So absorption peak, it changes its position depending on your availability of the silica in the rocks. Okay. So percentage of silica in the rocks. Now I am changing slide. Yeah, now you see here, this is an image of an area, Landsat TM, this pulse color composite 754. It shows you the three broad rock types. They are dark volcanics, This is the dark rocks, dark volcanics, and there are some of altered rocks, there are hydrated rocks, and these are the limestone hills, limestones. Okay, these are the bright, this one rocks. So they reflect a lot of this solar radiation, so that is why they are bright. Whereas these are your altered hydrated rocks, and these are the dark volcanics. Now in the thermal image, how they appear? The dark volcanics, it absorbs most of the solar radiation, so they becomes warm, isn't it? So the bright signature we get in case of dark volcanics. And altered, these rocks is made of hydrated rocks only, so there are a lot of water molecules are there. So water molecules again absorb solar radiation, so they have moderately bright. Whereas if you see the limestone, they are highly reflecting rocks, highly reflecting. So as they reflect most of the solar radiation, they do not absorb much of the solar radiation. Then they will appear dark. They appear dark in nature. See here. So these are all dark in nature. This is the zone. It is here dark. Isn't it? Now coming to the radar remote sensing or microwave remote sensing. Okay. There are certain advantages of radar. Okay. So so what are the advantages of radar remote sensing? Because it is active remote sensing, so it can operate both day and night time. Particularly in the polar regions, it is very much important, because in polar regions, there is part of the year, so in 3 to 4 months, it is dark, completely dark, isn't it? So during that time, this optical remote sensing is not possible. Solar radiation does not reach the polar regions. Okay, so that is the reason for that. Can be imaged by the radar remote sensing, because here the radar pulse or electromagnetic radiation is transmitted from the sensor, from the satellite itself. Then it is interacting with the Earth surface and it comes back. Okay, so active remote sensing. So it is very important for this day and night sensing and in the polar regions. It can penetrate through cloud. So that is the reason it is important for equatorial region. It can penetrate through dust and smoke. Okay, so see in a volcano, you cannot image. In an optical region, it is difficult to get your picture of this volcano. But whereas in the radar region, you can get a nice picture. And you see, this is this region in radar image, and this is the same in the optical image, almost covered by cloud. Okay, there is a statistics. It shows that almost 90% of the European territories. Okay, 90% of the acquired satellite images are cloud covered. Okay, so cloud free images are available only for a particular period that statistics was taken, and it was seen that 10% of the images are cloud free and remaining 90% are cloud covered. Okay, that is why this radar image is very, very important. And the another important advantage is it can penetrate through vegetation, so you can get the terrain information in a forest area. It can penetrate through ground, so you can get subsurface information like buried channels, like underground pipelines. So this kind of information also you can get in radar sensing. So we are interested in this particular class is on the geological features. So geological features like your buried channels, okay, or active faults, which is covered by the alluvium. So those kind of features you can get in case of radar image, but in optical image, no. That I will show you one example. Now, radar image has certain advantages, certain characteristics rather. What are they? Because sensitive to surface geometry, because it is radial or laterally looking off nadir. So it is very sensitive to surface geometry. So it highlights the geomorphology and geological structures. It is very sensitive to surface roughness because it is a coherent signal. Okay, so coherent pulse. So very sensitive to surface roughness. So non-vegetated terrains or rock types can be interpreted. It is very sensitive to soil moisture or moisture content or the dielectric property of the materials. So it is very, very important to identify unconsolidated material like alluvium, soils, and in geological applications, particularly identification of the bosones or altered should be identified very nicely. Okay. And most importantly, its capability to penetrate through vegetation and ground that allows to image vegetation covered terrain and subsurface geological features. As I already told you, buried channels, active faults covered by alluvium. So those kind of features you can interpret. And some kind of civil structures like water or oil pipelines, sewerage lines, that those kind of features also you can identify. Now you see, this is an area where the rock types can be very nicely interpreted from radar image. This is a radar image, a C-band radar image, okay, radar sat image. Here there are three kinds of rocks are there: limestone, sandstone, and shale. You know, limestone is very hard and compact, so your surface is very rough. When the surface is very rough, the radar return will be more and it will look bright. And sandstone is a medium-grained rocks, so here the intermediate surface roughness, so it gives you intermediate brightness. Whereas shale or clay is very fine-grained rocks, okay. So its surface roughness is very your low surface roughness, okay. So it is a smooth surface. So that is the reason it looks dark in radar image, okay. So based on the surface roughness, we can interpret this is limestone, this is sandstone, and these are shale. This is the interpretation. You can see here, this is the limestone, this is the sandstone, and these are the area made of shale or clay. Now we see if we can merge radar image with the optical image, like Landsat, this false color composite, or Astar false color composite, or IIRS list 3. Okay, so the kind of false color composite image, if we merge the radar image, then you see this your spectacular view. You get this color that is important for this separating the spectral signatures, the rock types particularly, and land use land cover types. Okay, depending on the color and composition of these features. But most importantly, when you merge radar image here, you get the information about the geomorphology very nicely, geological structures, okay, and some these subsurface features, and also see surface sensitivity. It gives you some surface. These features will be highlighted. Like you see here, you can see the dunes. The dunes you can see very nicely because it is radar image is merged. You can see this is an impact crater. So boundary of the impact crater is very nicely you can see. You can see there is a buried channel which is covered by this alluvium, loose materials. That is very nicely it can be interpreted because radar image is merged with the optical image, so it has highlighted that. And also geomorphological features, you see the level of dissection, okay, the ruggedness, the detail of the ruggedness, all the things are very prominent because of the radar image. This is this RISAT image of this Dhanbad Jharia coalfield. You see here we have two kinds of polarization image: the horizontal polarization or light polarization image, and cross polarization image or horizontal vertical polarization image. So what is the difference between these two polarization? This horizontal polarization, it gives you information about surface scattering, whereas cross polarization gives you information about the volume scattering. What does that mean? So surface features in a mining area like overburden dumps, like your settlements, or many kind of your mining installations, or the bridges, for example, they are very prominent surface scatterers. So you see the river bridge is very prominent. Okay, settlements are prominent, overburden dumps are prominent, isn't it? All the things are very prominent, along with this river bed and some of the quarries. But in the lower image, it is a cross polarization image. These surface scattering objects are not prominent; they are subdued. Even this river bridge, not even seen here. The river bridge is not vanished because the image is taken at the same time. Both the images are taken at the same time by our RISAT satellite, isn't it? RISAT satellite image. So both the images are acquired at the same time. But here, see, you cannot see the river bridge. But what are important here? You can see these quarries are very prominent here. But surface scattering features are not important. But in the next slide, you see very interesting. Here you see surface features are prominent. But in this case, cross polarized image, you see near surface or subsurface feature. What is that? Geologists can appreciate that. It is a fault which is covered by alluvium, which is covered by the soil, by land use practices. Okay, there agriculture is happening here. In case of HH, signature is very faint or it is not at all visible. But in a cross polarized image, this geological fault can be very nicely interpreted. Now coming to geomorphology. Okay, So geomorphology deals with the physical processes and materials in shaping the Earth's surface. Geo plus morpho plus logy. Geo means Earth, morpho means shape, and logy is science. Okay, so basically it is the science of the shape of the Earth's surface. Okay, so geomorphology is the science of the shape of the Earth's surface, and more precisely, it is your surface elevations, and this mostly it is reflected by the differences in the surface elevation. Okay, and here the unit of geomorphological study is a landform. And what is a landform? Landform is characterized by its unique topography, composition, and structure, and it is a multivariate feature. And what are those multiple variables responsible for this landform to develop? Here the rock types, geological structures, what are the geomorphic processes operating in this area, what is the climate and time. Okay, all these variables, all these factors combinedly gives you the landform. Okay? And why this remote sensing is important? Because you see here the remote sensing image, you get the synoptic view, you get the terrain elevation, isn't it? So terrain elevation, this information you can get from the satellite image as well as the digital elevation model. Okay, so that is the remote sensing provides synoptic view and elevation related information of the landforms that facilitate their recognition. And in geomorphology, we study the morphography, we study the morphometry or the measurements. Okay, then morphogenesis, how these landforms has been developed, and when they have developed, morphochronology and morphodynamics, how far they are active at this moment. So all those things we study under geomorphology. Okay. Now you see some important these landforms I will show you. You see this is, what is that? This is a monochromatic image of the Kosi fan. And you see the Kosi river, sometimes it was flowing here, sometimes it was flowing here, sometimes it was flowing here, sometimes it is flowing here. It is highly unpredictable. And why it is highly unpredictable? Because here the discharge is very much varying, and here the high relief and this high sediment load. Okay, so that is leads to its unpredictability of this Kosi river. Okay, and here you see this is a color image, false color composite image of the Ghaggar fan, Ghaggar river. Okay, so Ghaggar fan you can see here. This is a multispectral false color composite image, but it is covered by settlements. So if you walk over this area, you will not be able to understand what is there underneath. Actually, it is a fan deposits on the foothills. Okay, and in the remote sensing image, very clearly you can identify, you can delineate. Okay. Now you see here, it is a fluvial plain. You see the drainage. This drainage in the north is a Barak river, and you can see the oxbow lakes here, isn't it? There are some natural levees. There are sandbars, and here there are some paleo natural levees. This is the alluvial plain. If you take a extended view of this area, you can see like this. This is the alluvial plain. These are the oxbow lakes. This is the sandbar, and these are the paleo natural levees. So many features you can identify. Now you see some samples. Here you see this is the rock area. A number of river terraces can be nicely interpreted here. You can see this is another example. You can see the meander scroll, meander scar, very prominently you can identify. Here is this abundant channel. This channel at this moment, this river is flowing here. Water is not flowing along this channel, so it got abundant. But whenever there is discharge is very, very high, it can again flow through this line. Okay, so that is the reason this abundant channel. So there is the flood potential is very, very high in and around the abundant channel. Now you see here, this is the river, Barak river. I have already shown you in the previous slide. So it is, you see here, highly anomalous. It's a normal river, isn't it? So why it is so anomalous? Because in the subsurface, under the this ground, there is a geological structure. This domal structure is there, and these domal structures restrict the flow of the river. So that is why the river shows this kind of anomaly. And here you see, this is the Lucknow and Kanpur region. You see the paleo channel belt. So paleo channel belt what it suggests, that in this belt, this groundwater availability is very, very high. So you can dig a well here and you will get good water, underground water. Now, I am coming to some of the applications. To begin with, the groundwater prospecting. In groundwater prospecting, we do it by two kinds of approach. One is first order or direct indicators. So direct indicators, what are they? This is the indicators associated with the recharge zones like rivers, canals, and lakes and ponds. Then the features associated with the discharge zones like springs and other sites of effluent seepage. Then soil moisture and vegetation. So depending on the recharge features, recharge zone features, discharge zone features, soil moisture, and the relative vegetation density, you can interpret where groundwater prospect is high and where groundwater prospect is low or very low. I will explain one example. Now, second order indicators are topographic features, or the slope of the terrain, then the type of the rocks, essentially the hydrogeological properties like porosity and permeability of the rocks, then the regional structural features, then the fracture systems in the hard rock areas, then weathering depth, drainage density, and any kind of special geomorphological features like if there is any sinkholes that occurs in the karst topography, limestone terrain, or if there is an alluvial fan, if there is an oxbow lake, okay, as we have seen in the previous slide, if there is any dikes, if there is any lineaments, buried channels. So those features are very, very important to interpret where the groundwater prospect is high. Okay, valley fields, this dune complex, isn't it? So there are many features. Like here you see, this is the Piedmont or Piedmont alluvial region, the foothills of this Himalaya, or this is the Siva basically, and this is the Yamuna river, isn't it? So now you see, here the vegetation density is high, whereas here vegetation density is very, very low. Here is a bright signatures. So dry your rocks, basically dry, not rocks, the rock fragments, isn't it? Dry alluvium, whereas here it is the vegetation density is more. Here you see rivers are mostly dry, no water on the surface, isn't it? But here you see water is coming to the surface, isn't it? So here discharge is taking place. So these are the discharge zone features are visible here. Here recharge zone features are visible here. So here groundwater is deep in this region. Here groundwater is shallow. So you get more groundwater in this region than this region. Here, why? Because here surface water percolates down and it moves as a base flow. So as a base flow, it is coming here and it is finally it is coming near to the surface. Okay. So based on your first order these signatures or first order indicators, we can interpret the groundwater prospects very nicely. And then you can use all those second order these indicators, as I had told you, like rock types, like geological structures, like hydrogeological properties, as I have already explained to you. So by interpreting each of these indicator and then finally integrate them, then you can understand that where the groundwater prospect is high and where the groundwater prospect is low. And then this application is related to geological resource exploration or mineral exploration, okay, mineral or hydrocarbon exploration. So here, for example, this remote sensing can be very nicely used for this mineral exploration, like base metals, like your surface minerals. The minerals, those are exposed at the surface, isn't it? So here you will get the spectral signatures of the rocks because they are exposed at the surface. Sometimes by using the surface signatures, you can interpret what is there in the subsurface. Okay, and by GIS system, you can have a mineral resources information system. Okay, so from this mineral resources information system, you can have all kinds of this information regarding these mineral deposits, regarding the grade of the ore, regarding the occurrences of the ore, and different kind of mining related information can be stored and can retrieve by this button click what kind of information you need for mining or for mineral deposit. This related information can be available at any point. Okay, so that has been, for example, we have developed it for one of the area. Now, remote sensing is also very much important, particularly for reconnaissance of hydrocarbon exploration or petroleum exploration. For example, for identification of sedimentary basin, for lithological identification, geomorphology or terrain analysis, geological structures, tectonic information, and most importantly, this characteristic spectral absorption properties and hydrocarbon index is very, very important to interpret. If there is any seepage of hydrocarbons at any area that is onshore, on land, if the hydrocarbon seepage is taking place, then what will happen? Directly you can get these signatures of the hydrocarbon or oil, or it can retard the growth of the vegetation, or soil will be mixed with the hydrocarbons. So these spectral signatures of the soil will change, vegetation will be retarded. So from that also you can interpret this, that hydrocarbon is occurring or oil is occurring underneath. Okay, hydrocarbon index. I'm not going to the details. Here you see these different categories of hydrocarbon basins that ONGC have studied extensively, and they have identified different hydrocarbon basins. One is proven categories. One is this where this extraction is taking place, production is taking place, and then the second category is the identified and prospectivity, and this third and fourth, you see, it is the prospective. Okay, but more studies are required, and it is potentially prospective. So remote sensing is very, very important for reconnaissance of this site where hydrocarbons can be available underneath. And then you have to go for geophysical investigation, and then you have to do drilling. Okay, like you see, for particular example, you see here from the drainage anomaly. So from the drainage anomaly, you can interpret here that there are some geological structures is there which can potentially serve as a reservoir for oil. Basically, it is a trap for oil. Okay, so this kind of information you can get it as a reconnaissance information for hydrocarbon exploration. Then you have to go for geophysical investigation. Okay, like here seismic profile. You see the seismic profile. From that, we can interpret your faults, and this, you see here the top of the productive zones also identified. So this is done by ONGC extensively. Then this other kind of geophysical investigation, particularly your spaceborne geophysical investigation, is also very important. Here satellite gravity will be low, because where oil is lighter than even water, isn't it? So wherever there is oil accumulation is taking place, you will get this low gravity. So from this low gravity, and from these characteristic seismic signatures, and from this your geomorphic anomaly, all these one by one, step by step, you can identify that is the oil is there or not. Okay. Then by drilling, you can confirm that yes, oil is there. Now I am going to another application. This application on the geological hazards, it is a landslide study. So you see, this landslide is classified with the different criteria is used for classification of landslide. Depending on the type of the movement, landslide can be categorized as the faults, like rock faults. Then there is the topples, slide, spread, or flow. This is a detailed classification of landslide. Then depending on the material type, it can be rocks can be involved in the sliding. Then it will be rock faults, rock topples, rock slide, rock spread, flow. When it is your boulders or pebbles or gravels are involved, so we can generalize as debris. So then it will be called as debris faults, debris topples, or debris flow. Similarly, when it is very earth materials, fine materials, we call it earth faults, or this your earth flow or earth spread. So this is how we can classify landslide. Now, based on the activity, it can be active, it can be non-active, it can be active and it is non-active means old. It can be dormant as well. See it? Based on the geometry of the landslide, it can be planar, it can be rotational, it is curved, so many things possible. But how remote sensing is helpful in this landslide studies. So remote sensing is very, very important to identify the active landslides. This is the very, very overview kind of information you can interpret. You can do a lot of advanced studies with remote sensing. I'm not going to that. So first kind of information is identification of the active landslides. How? from the scar on the Earth's surface, you can identify the active landslides, where there is no vegetation. So you can do it by visual interpretation, simple visual interpretation, or some advanced digital image processing techniques like image segmentation or change detection, that is multi-temporal change detection. Before the landslide, if you have one image, and after the landslide, another image, and you study how this gray level of this pixel has been changed, isn't it? By that, you can also identify the scar very nicely. So active landslide can be identified based on that techniques. Now, old or dormant landslide, you have to use some kind of indirect signatures like break in slope, like accumulation of thick soil, like differences in the pattern and density of vegetation. So those kind of things you can interpret from satellite image, and from this information you can interpret that is the old or dormant landslide is occurring, isn't it? Now, potential landslide areas, for identification of potential landslide areas, these are some of the important factors. Okay, so there are a set of factors what you have to study individually, then you have to integrate by this your data integration techniques. Like here, the topographic slope is important. Then the this stream undercut, then this drainage concentration where the seepage is more, then the concentration of the weak planes like lineaments, fractures, see it? Then active landslides in and around that area or old landslides. So these are some of the very important factors, but there are many factors like what is the soil, what is the soil cover, what is the soil thickness, what is the vegetation cover, what is the slope, I have already told you, isn't it? So these are geological structures. All those factors are very, very important to identify potential landslide area. Okay? Then triggering factors like your rainfall or earthquake, seismicity, that causes the landslide. Even if this area is very, very vulnerable for landslide, but landslide may not occur unless the triggering factor is available. When there is a rainfall, is huge rainfall, prolonged rainfall, torrential rainfall is there, then what will happen? The land will be slided down, isn't it? Or there are a lot of shaking due to earthquake. That also led to this landslide or slope failure. You see some of the satellite image. Here, this is the photograph, field photograph. You see, this is a satellite image, and you can compare these two, isn't it? This is a rotational landslide. It's a curved plane. This hill slope has been slided, and this surface is curved like a spoon, isn't it? And it's slided down on a curved plane. So, and the remote sensing image, this rotation slide at Kandi, it can very nicely, you can interpret, isn't it? Now you see in case of Uttarkasi, we have studied in the late 90s and early 2000, we have studied in all along this your pilgrimage route corridors, like this road to Kedarnath, then to Badrinath, then Gangotri, then Jamunotri, and also some of the these your route corridors of Himachal Pradesh we have studied. From IIRS and many other organizations, the National Remote Sensing Agency, CBRI, Wadia Institute of Himalayan Geology, many organizations work together. This under the leadership of ISRO. Okay, and then these route corridors were mapped in terms of the landslide, this potential, a landslide hazard. Okay, so in this study, it was very nicely, it was interpreted that this Uttarkasi area, high hazard zone, where landslide vulnerability is very high. Anytime landslide can occur. And you know the landslide occurred in a few years itself, Gorunapat landslide, isn't it? That again we have studied, but here because this study was done in 1:50,000 scale. So that scale is not large scale, because if we want to characterize the landslide and for your subsequent your operations, we need high resolution images and for a larger scale this information. So for that we have collected this airborne your aircraft image, aerial photographs, very high resolution, 1 meter spatial resolution, and then we have interpreted immediately, just after the landslide occurred in the same year itself. So we have studied, and all the layers are what you can see here. These layers are generated after the Gorunapat landslide occurred. So this is the image before Gorunapat landslide. This is this LIS3 image, and this is the pan image, pachromatic image. You see just after the landslide, what is the signature, how it looks. Okay, then this we have studied it. And then large scale information we have this generated for this landslide. And there are many studies happened afterwards. And you see this is the view of this Gorunapat landslide. Now for geo environment, studies, like in case of mining, in case of this dam and reservoir, in case of tunnelings. Okay, so this kind of geo-environmental studies are very, very important. So this is one of such studies, the geo-environmental studies of a mining area. And you know this is the Dhanbad area of Jharia coalfield. See, here we have integrated optical remote sensing data, we have integrated thermal remote sensing data and microwave remote sensing data. All three sensors data we have integrated. This is a multi-sensor approach. And then we have prepared a surface plan where you can see the surface coalfire area, where you can see underground or subsurface coalfire area, where are the coal dumps, where are the overburden dumps, where are the open quarries, or where the open cast mining is taking place, where the quarries have been done, mining has been done, but reclamation has not been done. That means it is a closed mines, abandoned mines, but no reclamation. So that everything we have prepared using multi-sensor approach. Okay. So you see some of the field photographs. So this is the open cast quarry, Bansjora open cast mine. At that time, it is 15 years back story, 10 years. And this is the overburden dumps. You see, this is the coal fire, and this is your abandoned mine. This is the abandoned open cast mine. It's not reclaimed, isn't it? So this is water body has been developed. Okay, so more reclamation, maybe more beautiful landscape you can develop. But anyway, there's water is there, and so a lake has been formed here, so that this fire can be managed. But even then, there are fire here. This is why I am showing this mouse. Now, not only this kind of signatures, but also this in a mining area, particularly in the coal mining, there are a lot of land collapse takes place, land subsidence take place, roof collapse takes place, and that causes a lot of casualty. That causes loss of property. That is the reason we have studied the land subsidence of this area, so that we can interpret, we can identify the areas which is potential for roof collapse in the near future, where the land is subsiding at a very high rate or considerably high rate. We can tell that this particular area is more vulnerable to roof collapse in the near future. So this is the study aimed for that. Okay, you see here by this technique, it is a advanced technique like differential interferometric SAR, and advanced differential interferometric SAR can be implemented. It is simple differential interferograms only, and from that you can map these areas which is subsiding areas, and this is the rate of subsidence. You can see some areas subsiding in this particular your results up to 30 to 35 centimeter per year, whereas here you see even up to 55 to 60 centimeter per year some of the areas are subsiding. Okay, so we have to use this different kind of satellite data. Okay, because data is very, very important, and the processing. Okay, this some of the ground photograph you see. This is this area which is subsiding, or roof collapse is taking place due to the fire underneath. And here you see, here underneath, here the underground mining is taking place by caving operations. Okay, and there are big cracks. And this gentleman is from Survey of India. They have worked with us in a collaborative mode. They have studied how this land is subsiding. Okay. And this is another, this slide is for if you groundwater pumping induced this subsidence. So in an area, if groundwater extraction is very, very high, it's taking place particularly in some of the areas, even in the northwest India, groundwater depletion is very high, and we are studying that areas. We have studied, and some of the studies already we have published, and report has been submitted, particularly in the Mohali, Chandigarh, in Delhi, and some of the areas in the Gujarat also. They are subsiding due to groundwater pumping or due to the oil. Okay, so that study you have to do it for a area specific. Okay, oil is not much important because it is taking place on a very deeper level, but groundwater pumping is taking place in northwest India, particularly in Punjab, Haryana, Delhi, and Chandigarh. So these are the areas. Okay, and this your western part of UP and is the northern part of Rajasthan. So these are the areas that are very much groundwater depleted region, where groundwater pumping is taking place or taken place at a very high rate, and this is highly depleted zone. Here land subsidence can take place in many of the areas. We have studied only few of such areas. Now you see one of the example, it is not in India, is a Bandung city in Indonesia. See, here volcano is very, very important. All these volcanic cones, okay? This is at the periphery, there are the volcanoes. There are all, mostly there are all the old volcano. And here the city is here. and here the lacustrine and the volcanic deposits are there. And here for the city, the pump water is so much so that you see there are the land is subsiding is such a high rate. This is a groundwater pumping rate, and this subsidence is up to 20 centimeter per year in these areas you can get. Also, you can use remote sensing for studying the seismicity or earthquake. Whether if there is any earthquake takes place, you can measure how much displacement has taken place, how much shaking has taken place. That also you can study remote sensing techniques and some of the geodetic techniques. And also during the interseismic period, when there is no earthquake, how this earth crust is getting deformed, how the strain is getting accumulated, that also can be studied. And that is very, very important for understanding when earthquake can take place, where earthquake can take place. Okay, so but if you tell when earthquake can take place and exactly which place, it is very difficult, because you know earthquake prediction is not a very easy job. But people are working towards that, which is the likelihood area where earthquake is more likely to occur, which is the likelihood area, which is the likelihood time a particular area, okay, when earthquake can take place. But this science is still lot of studies are required. But likelihood areas is to some extent is possible. But there are some short-term precursors can be studied, like if there is any thermal anomaly, if there is any ionospheric disturbances, okay, from that, these anomalies, you can say that in the near future, in a few days itself, earthquake can take place. Okay, so these kind of studies are there, but how far this is reliable? So that is people are working on that, and in many cases, it confirms that the science is getting day by day, it is getting more and more. It is getting confirmed that these precursors are working well, working fine to forecast earthquake. But one individual precursor may not be enough. You have to study a number of precursors, and then you have to, based on the number of precursors together, you can interpret or you can suggest that earthquake can take place in a particular area. Okay, and this is the image you can see. This is just in the 2015. There in 25th of April. There is the earthquake took place in the Nepal. This Kathmandu. That is the Gorkha earthquake. 7.8 magnitude earthquake occurred, and many 6 and above magnitude earthquake occurred afterwards, and one 7.3 magnitude earthquake occurred is very near to this your main shock of 7.8 magnitude. 7.3 magnitude earthquake occurred in Kodari village, that is 140 kilometer east-southeast of the main shock. Okay, so this earthquake displacement can be studied. This is one of this picture you can see from the satellite image. This is the technique is known as this ScanSAR interferometric SAR. Okay, so from that we can see the displacement very nicely. Here along the radar beam or line of sight displacement is around 165 centimeter of uplift took place and 60 centimeter of subsidence took place. In this area subsidence and in this area uplift. Yes. With that, I conclude my lecture. Now I welcome for your questions and we'll discuss. So as many as questions will come from you, we'll discuss on that.